Hello, friends. Today we have AI for the tutor. S is for supervised learning. I'm Dr. Sonali Tamhankar, and this is our AI A to Z series. Remember when we had to enter those 4-digit codes at the grocery store checkout to identify produce? Not anymore. We let the scanner do the work. So, what's actually happening when you place apples on the scanner and it immediately says Honeycrisp? This is an example of supervised learning. How does it work? At its core, supervised learning always follows the same structure. We have a problem. What do we want to predict? The target variable. We choose features. What information will we use to make that prediction? And we need labels, the correct answers that the model will learn from the tutor. So, in our example, the problem is identifying what is placed on the scanner. The target is the produce type, Honeycrisp, Fuji, Gala apples, or carrots or potatoes. The features might include the image of the produce, maybe the weight. So, how does the system learn this? It is trained on a labeled data set, lots of examples of produce, each paired with the correct label. Because the training data comes with known answers, this is called supervised learning. Earlier in this series, we talked about clustering, which does not use labels. A clustering algorithm might group apples together because they look similar, but it wouldn't know that one group is Fuji and the other is Gala. To name things, we need labels. Once the algorithm is trained, it can predict the target variable for input features, like the apple on your scanner. So remember, AI is an umbrella term, and under it may sit many different ideas, from simple rule-based systems to machine learning to generative AI, even robotics. The term supervised learning is most often used in the context of classical machine learning. So let's look at a few more examples in this category. The iris dataset is famous in data science. It has 3 types of irises, and for each flower, we measure 4 features: the petal width, petal length, and the sepal width and the sepal length. The target variable is the iris species. Note there are no images here, just the 4 numbers. Compare that to the grocery store example. So even a 256 by 256 image already contains over 60,000 pixels, and each pixels has the RGBA value. So the number of features is vastly different between the two examples, but it's the same supervised learning structure. Or consider a student's exam score. We could pretend for simplicity that the exam score depends solely on the hours studied. So that's a supervised learning problem with a single feature. In healthcare, we have rich data: patient age, lab values, vitals, diagnosis. Suppose our problem is predicting 24-hour sepsis risk. Sepsis is a critical life-threatening condition where every hour matters. The features come from patient data up to a certain point in time. The label or target is whether the patient develops sepsis the next day. Again, same structure, different domain, higher stakes. Early warning sepsis prediction systems embedded in the clinical workflows have saved lives. Now, let's look at use cases that combine traditional machine learning with other approaches. I have linked a fascinating 60-minute segment below about the Atlas robo from Boston Dynamics. In one part of the segment, a researcher wears a VR headset and teleoperates Atlas to demonstrate tasks like stacking cups. These demonstrations provide labeled examples of what the robo should do, a form of supervised learning. In another part, Atlas learns to do jumping jacks. This is closer to imitation learning. A human wears sensors to demonstrate motion, but Atlas has a different body. So it must adapt those movements within its own physical constraints. This training also uses reinforcement learning. Thousands of simulated atlases try jumping jacks. If they fall, that's negative feedback. If they succeed, that's positive feedback. Over time, the robot learns which actions lead to better outcomes. So these methods, supervised learning, imitation learning, reinforcement learning, can be combined for complex problems. Let's talk about a bottleneck now. Labeled data is the gold standard for supervised learning. And like gold, it is expensive. So having human label apples does not scale. Getting labeled data in healthcare often requires expert clinicians and their time is precious. So sometimes we relax our standards. Weak supervision uses proxy labels that are correlated to what we care about but imperfect. For example, we might want to model true patient sickness or disease severity, but instead use healthcare spending as proxy. So sicker patients often get more care and have bigger bills, so such proxies can work, but they can also produce bias because patients who are sick but can't afford to get care aren't well represented, for example. There are other creative approaches too. In the world of generative AI, knowledge distillation uses a large, powerful model like a big LLM to generate labels for a smaller model, such as one that needs to run on your phone. So the large model acts as a teacher or a tutor, scaling supervision far beyond what human alone could do. We can also use soft supervision where labels can be uncertain. So a grocery scanner might not be entirely sure whether something is a Fuji apple or a Gala apple, and it may estimate probabilities, sometimes asking you to make the final call. In self-supervision, which we discussed in F is for foundation models, the data provides its own labels. So when a language model looks at part of a sentence, Winnie the Pooh reached into the jar of, the next word in the text itself supplies the answer and is treated as the label. So traditionally, machine learning problems, supervised machine learning problem fall into two categories. Classification means predicting a category like Fuji versus Gala versus Honeycrisp. And regression means predicting a continuous value, exam score or house price. There are many algorithms to do this. Linear regression fits a straight line. For example, exam score as a function of hours studied. Decision trees are another algorithm that typically ask a series of yes or no questions. Suppose we want to predict home prices. The model might ask, does the house have more than 2 bedrooms? Was it built before 2015? So to predict the price of a particular home, we follow these branches and then average the prices of homes in the training data that meet those same criteria. The decision tree algorithm skillfully chooses branches that best separate different data points. Random forest consists of many decision trees. The idea is to improve accuracy and stability by averaging their predictions. An ensemble approach that's loosely similar to the mixture of experts models in modern LLMs. Then k nearest neighbors make predictions by looking at the nearest data points and either averaging their values or taking a majority vote. There are other important algorithms like logistic regression and support vector machines. Logistic regression is interpretable. Its coefficients show which features are most predictive of the outcome, and support vector machines are a highly successful class of algorithms that work by maximizing the margin between different classes. So these methods have been the backbone of machine learning for decades, and they remain highly relevant today. For example, in the sickle cell project we discussed in R is for retrieval augmented generation, I started with a supervised risk model to predict emergency risk before layering on the generative AI capabilities. So AI relies on many paradigms. We discussed the supervised, unsupervised, reinforcement learning. Semi supervised learning combines supervised and unsupervised learning ideas. And in active learning, a model asks humans for labels only when it is most uncertain. The funny thing is, learning about artificial intelligence is a great way to appreciate human intelligence that has yielded so many brilliant ideas and algorithms and approaches. So, that was supervised machine learning, learning from labeled data. We talked about labels we can use when we can't have gold standard, and we saw so many examples of supervised machine learning problems and algorithms for classification and regression. That is it for today. Tomorrow, we'll dive deeper into the issue of training data. AI is shaped not just by algorithms and compute power, but perhaps most critically by the data we train our algorithms on. This deserves a whole separate video. So, see you tomorrow and bye.